So this is looking at the image formed by convex lenses, part 2, where we consider now what would happen if we move the object inside the focal point. So for illustrative reasons, I've decided to make the focal point here twice the focal distance from the previous examples. So instead of 3 centimeters, it's going to be 6. And that's so that we want to kind of just have a bit more room to look at ray tracing within the focal distance. But we're going to approach the analysis identically and see if this matters. So previously what we had looked at was this case where the object was 8 centimeters away and a 3 centimeter focal length. So quite a bit farther out. So let's see if anything changes this time. Okay, so again, we're going to do this 2 ways. We're going to look at what's going to happen through ray tracing and then calculating. I'm going to note here, and I guess I'll do it below, that the height here hasn't changed. I'm still going to use a 2 centimeter height. All right. What about the distance away? Well, that's actually going to be, let's take a look, 2 centimeters as well. Alright, so let's get into our ray tracing. What's going to physically happen to a variety of light rays, and how does that map out the image? The first ray that would be helpful is going to go from the top of the object and be parallel to the optical axis. And so again, as we've seen before, it's going to then be refracted such that it travels through the focal point. All right, and the next one that we can easily draw is from the top straight through the middle of the lens so that it doesn't actually change trajectory. Now, what else can we do? Originally, when we did an image ray tracing where we were outside the focal distance, the next ray we could draw would be through the focal point on the same side. But that doesn't seem very helpful in this case. But in fact, that's sort of what we're going to do. What we're going to do is consider what ray would go to the lens and then end up perpendicular to the optical axis. And the easiest way to do that is to consider the ray reversibility means where is the ray that would come in from the right that's parallel to the optical axis and then go through the focal point. So we're going to work it out this way. And then it's going to be parallel to the optical axis. And I'm just going to go back and get rid of that part. Okay, so I'm just going to add little arrows. So how does this tell us where the image is going to be? Well, in this case, we're going to have to do something a little bit different. And that is, noting that these lines do not converge on the other side of the lens, in fact they diverge, what we're going to do is trace them, these refracted rays, we're going to trace them backwards. And so let's start with that latest ray since it'll be relatively straightforward. We're going to go from that point here and go straight back. So it'll be parallel to the optical axis. And then let's go to the next one. And then we'll go to the last one. Now notice that these lines are all going to converge to a single point. And so that is going to be how we find our image. Let's now do what we did before initially and grab our original object and see what we're being told from the ray tracing. Well, we're being told that the object will be located farther away from the lens than the original object. We're being told the orientation is the same, upright, and it's going to be bigger. So there's our object. Okay, so we know now what happens when you have an object inside that focal distance. Let's now confirm what we could do by measuring. So let's just say these values here. We've got a distance to our image, S prime. And we're also going to have an H prime. So let's find those through a calculation using the thin lens equation. Alright, so it gets set up exactly the same way, where we have an equation for S prime, which is SF over S minus F. Except the numbers are a little different this time. We have an S, which is our distance to the original object, of 2 centimeters, an F of 6 centimeters, and so we get an S primed that's equal to, well, it's 2 times 6, which is 12, minus, divided by 2 minus 6, which is negative 4. And so we get a distance to our image of 3 centimeters with a minus in front. And the minus in front is telling us that we're on the same side as the original object. Okay, so we've got a S prime here of minus 3. All right, so now, and I'll just make a note of this minus sign thing for clarity. Okay, So that's what the negative means. Now let's determine the magnification factor. So our magnification factor is going to be, like before, this m value is equal to minus s primed over s. So in our case, we have minus 3 over s, and which was 2. So now we have a magnification factor of 1.5. And that looks about right when I look at the relationship between the two heights of the first object, which is 2 centimeters, and the image, which even to my ruler here looks to be 3 centimeters. Okay. So then if we want to get the height value, then we're going to multiply that factor by the original height of the object. So our h prime is going to be the absolute value of the magnification factor times h. So 1.5 times 2 centimeters. And of course, our magnification factor in this case was positive, which means that we are upright in the image. And so that's how we analyze convex lens images produced when the object is inside the focal point. And that's it.